Okay, we're going into one of my favorite subjects this week, thunderstorms and then tornadoes. They're kind of related, so we'll see what we can get out of that. So what conditions in the atmosphere favor the development of severe convective weather systems? So let's just look at a typical thunderstorm. Say you have an individual, one thunderstorm popped up today, happens in the summertime all the time. What happens? Well, air parcels, remember we've talked about them now for several weeks. They wind up being warmer than the surrounding air. Something pushed them up. Maybe a front started going up, but they wind up having a little bit warmer temperatures. And notice in this one, for example, that the air parcels, 32 degrees, actually bowed upwards where that warm air parcel is rising. So the initial, when you look at a towering cumulus cloud, what you're seeing is warm air rising compared to the surrounding. At some point, you wind up with a thunderstorm. The top gets so heavy, and remember, it's cooled and cooled to where it finally reaches the same temperature or maybe even slightly colder, maybe because the air was rising so fast than the surrounding air. So it is now stable. What's it want to do? It wants to fall back. You've produced all this moisture in that cloud, and what it does fall back as? Falls back as rain eventually. And you can see rain is actually going to push the air down. It's cool. Condensation is a warming process, but evaporation, which is taking place where the rain is in the cloud-free air, is a cooling process. So your temperatures are cooler in the rain. That's why it cools off when the rain hits you in a thunderstorm. And notice, ahead of the thunderstorm, air is rising. Behind the thunderstorm, the air is falling. And eventually, all you wind up with is some rain left over, maybe a light shower, and that is the whole thunderstorm process. Typical thunderstorms that develop like this last anywhere from 30 to 50 minutes. And you're done at that point. The thunderstorms can form different ways. We just looked at the single one. So you have a cluster of them or a line or in very intense supercell, which is very different. You can see here that with a cluster, you have different cells that are characterized by different development. As they develop along the thing, they begin to develop usually on the south side where the most moisture coming in and the heat is, to the north side where there is less of that, where they'll eventually dissipate. But they're constantly going through different phases. So you're looking for thunderstorm development where there's a maritime tropical air which can be destabilized by some kind of uplift. Usually a front, sometimes mountains, sometimes a sea breeze. And solar heating does drive it. So guess what? The hotter the day, the stronger your chance for heavier thunderstorms is. And that's why a lot of times in the Midwest, when you get severe weather, you've had a bright, sunshiny day all day, temperatures have climbed and climbed, and all of a sudden, the first cumulus clouds start to form. And because you've had all that heat to be released, they finally made it to a point where they can rise and keep on rising. And remember, unstable air keeps going up faster and faster, just like a hot air balloon that's hotter than its environment, rises steadily faster. So that air is constantly increasing then. And you can see here where most thunderstorm days are. They're down towards Florida. And guess what? Florida has that peak. It's almost always in a maritime tropical air mass. And you have sea breezes coming from the Atlantic and the Gulf of Mexico, causing thunderstorms when they converge, because that lifts the air up. And whether the sea breeze on the Atlantic side is stronger, it might push more thunderstorms to the west. Maybe the Gulf Coast side sea breeze is stronger, might push them to the east. But even up in Alaska, there are some thunderstorms. And there you can see what we just talked about with Florida, or the Rocky Mountains on the front range of the Rockies, where they have a differential heating. One of the other things with severe thunderstorms is they must have at least 58 mile per hour winds or hail greater than 1 inch, or producing tornadoes. That's the criteria. Guess what? Lightning's not in that criteria. So we have a lot of people that call the weather service when I was working that would tell me, boy, is there a lot of lightning. Yes, but it's not a severe thunderstorm. Lightning does not make it a severe thunderstorm. Lightning can kill you, but it's not severe. Wind shear is what dictates how severe a thunderstorm can be. Why is that? If you have the right wind shear, usually at least 40 knots of wind shear, it can help build the updraft and keep it going in the vertical instead of tilting to one side or the other. And by doing that, it allows the moist, humid air to continue to go up that column, and instead of the cold air that comes down behind it keeps pushing out, trying to get underneath that moist air, it doesn't happen. So you wind up with hot, humid air continually rising, and you sustain a thunderstorm for quite a long time. This is a synoptic pattern. You're going to get asked this question. What does synoptic pattern look like in the Midwest that causes severe weather? And what it is you have a very low-level jet coming out of the Gulf of Mexico, typically have a low up over Kansas with a cold front to the west and a warm front coming out to the east and southeast from that low. In the warm, humid air, you have the moisture coming up from the south in that low-level jet, and from the west, you have some kind of strong upper-level jet. And that causes tremendous wind shear. Wind shear is just changing direction of wind. Well, you have wind coming out of the southwest here, wind coming out of the south here, probably 70 or 80 mile an hour wind this way, 30 or 40 this way. So you're getting both wind change and wind direction. So that makes it very favorable to have tornadoes or severe weather. This is what happens in the Midwest many times, even in the East, where you get a little bit of an inversion, a stable layer, maybe 4,000 feet up. And it takes all day of the sun's heating or a cold front coming in to push that air that's heated up below it through that layer. So when you get that, that's a wonderful thing to allow temperatures to rise during the day, but it can be a trigger for severe weather developing in the afternoon sometimes. Or, if it's strong enough, it keeps any thunderstorms from developing. Within a cloud, there is things called graupel, which are basically like ice crystals that are beginning to melt. And they can change the charge depending on the temperature. Weird. To me, it's very strange that graupel becomes negatively charged if temperatures are less than 5 degrees. And if they're greater than 5 degrees, it becomes positively charged. And the ice crystals that are pure ice change charge as well at those things. So what that does, because now you have very strong updrafts and downdrafts in a thunderstorm, is pulling graupel around and it's pulling ice crystals around. And it's setting up graupel's a little bit heavier than ice crystals. So it's setting up a charge difference between different elevations in the thunderstorm. And that's where you're getting the lightning in it. And you can see it here in the image. Another part of a thunderstorm is the downdraft. That downdraft can be fairly small. It used to be many times you'd never detect it at airports. And that would cause aircraft to have all kinds of problems. Aircraft want to descend coming into the wind or take off going into the wind. So the aircraft is descending, the wind's blowing towards it. That helps to keep it aloft. If you get stronger wind blowing towards it, it's going to actually tend to help the aircraft to rise more. You have more wind going across the wings. Now, all of a sudden, you go on the other side of the downdraft. You have wind from the back side of it. You don't have much air going across the wings anymore. And what happens is the aircraft's going to want to go down to the ground very fast. Sometimes you get little microbursts that actually can occur literally on just a small part of a runway. So that as an aircraft is landing, it thinks everything is fine, and all of a sudden it has to deal with this microburst. And that can cause major issues for an aircraft. That's why a lot of major airports now have what they call Doppler radar that are for microburst specifically. They're put on there by the FAA, and they look for these small signatures. And sometimes you have a whole bunch of places along a runway that have wind direction and wind speed that are constantly being recorded. They can help detect these so that the aircraft, as it's coming in, will have a signal that these are occurring. And might be a problem. Another kind of weather event is the derecho, which is just a straight line downburst of winds and a cluster of thunderstorms. You've had these go through Ohio. At times, they have to travel at least 240 miles. And that's pretty daggone far, but they do occur. And sometimes there were 3 derechos in the summer of 2012, for example. And I can remember driving through one as I was driving into West Virginia, and it went through Ohio before that. Numerous trees were down, tremendous amount of wind. I actually looked for a place to stop. It hit me in Lewisburg, West Virginia, and I was heading to Hurricane, which is just on the western side, almost to Huntington. That's where my in-laws are from, and I wanted to get there. And we pulled off to the side of the road, and we had to wait till the wind died down. And then I went back onto the interstate and had to dodge trees the whole way because the lights were out all the way. It just so happened my in-laws had electricity, so we went there. But it took a lot longer than it normally would. And here you can see how a derecho would look. And here you can see the notable derechos and stuff that have occurred within 24 hours sometimes. Flash flooding. Think about it. You have all this tropical moisture getting pulled into these thunderstorms. And if these thunderstorms aren't moving and they happen to sit over the same area, you can get tremendous rainfalls from them. And that's where things like the Big Thompson Canyon and all occurred. Hail is just frozen into lumps of ice. What happens is you got that downdraft right next to an updraft. Some of those ice water particles get sucked back into that updraft, go back up, and freeze. And if they keep doing that, they get big enough, and you wind up with hail. And one of the beautiful things about dual pole radar is I can detect this. We talked about it earlier. There's a change in shape that occurs with the ice crystals like this. And when I can see that change in shape in a cloud, then I can put a warning out that there's a hail shaft that has developed and will probably eventually come down to the ground, maybe 5, maybe 15, maybe even 20 minutes later, but it can be issued a warning for it. Tornadoes, extremely violent. They have a very, very tight pressure gradient within them that causes that strong rotation, strong centripetal force. Usually they strike in very sparsely populated areas. And tornadoes, we rate them by EF scale now, which is enhanced Fujita. That scale was actually developed between meteorologists and civil engineers so that when you look at damaged structures, you can tell how strong the wind likely was that caused that damage. And then you can estimate the wind speeds. Tornado Alley is basically in the Midwest, Texas through Oklahoma, Kansas. There is another one they call Dixie Alley, which is in the southeast, Mississippi, Alabama, Florida. Timing of the major thunderstorms and tornadoes in those areas, Dixie Alley may be starting just a little bit earlier than the Tornado Alley. But both get tremendous amount of major thunderstorms and major tornado activity in the springtime. And some in the fall time as well. You can see here the number per state. States are kind of bigger. But and here's the divided by square miles. And you can see the most typically are in Kansas. But look at Dixie Alley too. 10, 10, 10 Florida per 10,000 square miles. So these are the areas. Now, if you live in Ohio, you still get a decent amount. And this was the Joplin tornado. And one of the interesting things about the Joplin tornado, it formed west of Joplin, and to the east it became an EF5 tornado and went through and caused major damage. It was so well spotted on radar. The warning was actually issued when that thunderstorm was out here and in Kansas for Joplin. It was literally parts of Joplin that had an hour to an hour and a half lead time. The question became, was that too much lead time? Because there were people in the eastern part of Joplin that actually decided, oh, we haven't seen it. We're getting outside of the restaurant we were in or we were sheltered because we haven't seen anything. And that was when the tornado occurred. Even though the warning was still up, they assumed that because it had been up so long that it was done. Again, interesting question for sociologists. And here is the enhanced Fujita scale. One of the interesting things, supercell thunderstorms are a single thunderstorm, but they maintain themselves because of the wind shear for tremendous amounts of time. Sometimes you can track supercells for hundreds. Even some have been known to go almost 1,000 miles across the United States. And here you can see a wall cloud. What a wall cloud is there's usually rain near it that has come down, moistened the air. Then that cool, moist air has been pulled up, and it creates literally a flat surface, usually rotating, in which eventually a tornado will pop out of. Above that, there's a mesocyclone that can be well distinguished, usually on radar. Not all mesocyclones form tornadoes. That's one of the issues. So always an issue whether you're going to actually have a tornado out of it. And here you can see a well-defined mesocyclone as it flucks Birmingham. Right in here you can see tremendous wind towards the radar, tremendous wind away from it, right next to each other. Outstanding signature. And you can see how it curves around like a mesocyclone is basically a meso low right in the thunderstorm there. They are characteristics of a supercell tornado or thunderstorm. So one last thing, I'm going to go through this pretty quickly here. There is a severe thunderstorm watch out right now. So it is out in Michigan. Well, not that far from Ohio. Here's the line of thunderstorms that you're seeing develop. The watch is out in this area. So why is that watch there? Well, what did we just learn? We want something to cause the air to rise. Well, I got southerly winds, southwesterly winds here, northwest winds here. So I've got converging winds. What else do I got that might go along with that? Well, how about some moisture? So you look at dew points. Wow, lots of moisture coming up here into this area and some warm air as well. So I've got a lot of moisture coming in there. So that's two ingredients I'm looking for. What else? Well, maybe I want to see how much convergence, something called moisture convergence. Right along that line of thunderstorms, very strong moisture convergence. That is taking into account converging air and moisture coming into that area. So good lift, plenty of moisture to work with. We're getting somewhere here. What about a loft? Does that convergence continue, or maybe there's divergence aloft? Yeah, I have very good lift all the way up through the atmosphere here. Finally, what about stability? Well, there's a measure of stability called CAPE. CAPE is the potential energy, convective available potential energy. So the higher that value is, the better chance the atmosphere is unstable, and maybe you can tap into it. And here CAPE is 2,500. I would consider anything that has decent lift above 1,500 to be a problem. And actually down here, there's 3,500 CAPE. So we've had very warm, moist air down in here being pulled into this system. Outstanding CAPE to work with. What about wind shear, which was the final piece that we talked about? We need a good wind shear to keep a system going. There's 40 knots of wind shear, not the best, so you're probably not going to get supercells, but you might get some damaging hail, probably some severe downdrafts coming from it as they're moving through. So that is why that watch was issued there. Everything we just talked about, looking at it in real time right now. So hope you got something out of this. Let me know if you have any questions.